Hi everyone, and welcome to the power of a point. Hopefully you have successfully created this diagram in GeoGebra and you've been able to explore a little bit what the power of a point theorems are all about. Here is the two-chord version, the chord-chord intersection version, and what that says is that the product of AX and XB is equal to the product of XC and XD. So we have those products down here, and you can see that in fact those two products are equal. As we move the point X around, or the point A around, or the point C around, we see that the product changes, but the two products are always the same. And that is the true nature of the power of the point. This is the two-chord version. There's also a two-secant version, so quite remarkably, this idea holds even if the point is outside the circle. Again, XA times XB is XC times XD, and you can see that here. And then there's even this secant tangent version. So I'm trying to make A and B coincident here. And the power of a point theorem says that XD times XC is the same as XA times XB. But if A and B are coincident, these are the same. So you just square XA, and that gives you this version of the power of the point. So it's really three theorems that sort of fall under this one umbrella of power of a point. And I'll come back to that in a second. But what I want to do first is just talk about how you prove these theorems. And it's relatively straightforward if you turn this into a triangle problem. So as I suggested, uh, most high school geometry problems are fundamentally problems about triangles. And so if you add these chords in, A, C, and D, B, you can kind of see the situation. Now you have these two triangles, and these two triangles are going to be similar. And they're similar because these angles are congruent because they intercept the same arc. And we know that two inscribed angles intercepting the same arc are congruent because each of their measures is both half the measure of that intercepted arc. So these two angles are congruent. These angles here are vertical angles. They're congruent. So by angle, these two triangles are similar. Of course, these angles are congruent because they too intercept the same arc. But anyway, these two triangles are similar. And you can set up a proportion like AX is to XD as XC is to XB. And then you could cross multiply and get the fact that AX times XB is equal to CX times DX. So that one establishment of similar triangles gives you the proportion you need to prove power of a point. Now, if you're outside the triangle, the same argument holds. You just have to construct different uh, segments. So now you construct BC and AD. These two angles are congruent because they intercept the same arc. This is a shared angle in both triangles. So triangle AXD is similar to triangle CBX. Then you pull the proportions out that you need, and you can establish again the power of a point formulas. And so all of these results are just straightforward applications of similar triangles. Um, so lastly, just to close, I want to talk a little bit about this idea of the power of a point. So it's really, there are these three theorems, but really this is about this point, x, and its relation to the circle. And what it's saying is that there is like given this circle and this point x, there is a number associated with it. It's the number 90.6. And it's this number down here. And regardless of where this point A is, that number is always 90.6, wherever this point C is. That number is somehow attached to this point, and that's the point's power. So no matter where you put this, that number is always 90.6. And it's always the product of the distances from x to both sides of the circle, from x to the far side times x to the near side. And that idea holds true inside the circle as well, the product of x from one side and x to the other side. And that's always the same number, regardless of which direction you take to get to the two sides of the circle. So that is the power of a point.